All right, so our speaker today is Safiyah. Is that the best?
Safiyah.
Okay, Mohammed. She earned a PhD in chemistry from the University of Illinois at Urbana-Champaign, one of the top chemistry universities in the country, where she focused on the development of first-row transition metal catalysts for hydrogenation chemistry. Who did you work with there? Who did you
With
do?
Allison Fout.
Allison, Allison who?
Allison Fout.
Felt. I gotta look her up.
Yeah, she's now at Texas A&M.
Oh, she's down at, oh, okay, okay.
Yeah.
So then Dr. Muhammad moved to and moved to uh, Michigan. So we were talking about this earlier. She's originally from Florida. So somehow you like the Midwest.
Yeah, somehow.
You went to Illinois, then you got a job at Dow Chemical as a senior research specialist in the performance silicones business. Her work focuses on development and application of new silicone resins for superior performance. Outside of her work, she is an active member of organizations within Dow and community-based organizations, and serves as the president to the Midland Professional Nomenclature chapter, which is the national organization of Black chemists and chemical engineers. And her topic today, you can see here, from quartz to computing, the origin and role of silicone materials in electronics. Thanks for accepting our invite, and we look forward to your talk.
The pleasure is all mine, and thank you for such a kind introduction, and thank you for inviting me. So today I'm going to talk to you all about some of the research that we do here at Dow in our business, Dow Performance Silicones. We'll talk about silicone polymers, how we get them, and one of their uses in this space of electronics. So again, my name is Safiyah Mohammed. I joined onto Dow into the Dow Performance Silicones group. So before we get into the technical, we'll talk a little bit about me. I'll give you my introduction. So I was born and raised in North Miami, Florida. I went to undergrad there close to home. Went to Nova Southeastern University, where I received my bachelor's in chemistry. And from there, I learned about graduate school. And so I applied to all of the top schools in inorganic chemistry that had a program that I was interested in. And some way, somehow, I ended up in the University of Illinois at Urbana-Champaign. So there I did my PhD work under Allison Fout, and I studied cobalt catalysts. So we focus on first row transition metal catalysts in that lab. And I studied cobalt catalysts and hydrogenation chemistry with the focus on increasing the signal to noise ratio in techniques like NMR spectroscopy with a special type of gas called parahydrogen. And
So
as I end, oh, go ahead.
before you finish this first slide, please don't skip over that. Looks like you're wrestling.
I'll definitely get into that. So before, when I got close to ending my time at the University of Illinois, I learned about the Dow Best Symposium, and so it was a space for me to learn more about what life in like industry was. And so through that, I got exposed to Dow, and eventually ended up here in 2021, where I joined into the product development group for silicone resins, coatings, and adhesives. And so in short, in that work, what I do is I develop new silicone resins and apply them in different applications for better performance. So outside of work, I am extremely active. So these are pictures of things that I enjoy or things that are important to me. So I have my family here. We recently had a trip. So we got to take a nice group picture. But you can see I really enjoy rock climbing. I enjoy weightlifting. I love eating. I love board games. I love being outside in nature. And I recently started jujitsu. So that's what the wrestling picture is. And yeah, I'm a white belt rolling with like a fourth striped brown belt. So almost to a black belt. And I was trying to hold my own. But yeah, that's me. And yeah, now we can get into the technical stuff. So the goal of this meeting is to just explain more about our silicone polymers, where they come from, how do we get them, how do we make them, and then after we make them, thinking about the structure-property relationship, right, and how we can take these silicone materials and apply them to various applications. And then we can also talk about how we actually take the material that we can make inside of our lab and translate it into a cured product that we can actually use. So before we get into that, I'll just briefly mention, at Dow, we're a pretty big company. We have a lot of different technologies that we work with. And so silicone only represents one of the technologies. But regardless, we're still one Dow. And so we actually collaborate a lot within our organization, across organizations, to use the toolkits that we have at Dow in order to solve problems for our customers. And one of the things that is top of mind for our customers and for Dow as well is sustainability. And silicones really allow us to position ourselves to generate some very sustainable products and allow our customers to meet their sustainability goals. So you can find us in spaces like mobility, consumer electronics, and personal care, building the infrastructure, with all of the goal being to make more sustainable products. So why silicones? There's a lot of different polymers out there. And so the question naturally comes up, why would we use a silicone materials? And so in order to answer that, you got to start thinking about some of the properties of silicones, right? So we know that silicon on the periodic table is in the fourth group. So we often will compare it to carbon. And if we think about carbon-based polymers, right, you start thinking about bond energies, bond length. And so if we start comparing the backbone of a silicone polymer, which is always a SiO-Si bond, so a siloxane bond, you start to see that the silicon-oxygen bond is far stronger than, say, a carbon-carbon bond, which you would find in a carbon polymer backbone. We also take advantage of the geometry, right? So if we look at the bond angles of that siloxane bond, you see that they generate much wider bonds than, or much wider angles, I should say, than your carbon-based polymers. And so it's mainly these two properties here, which we utilize in order to get certain characteristics out of the polymers. So with the bond angle being so wide, you get a much more open, flexible, mobile backbone, which translate into properties such as low surface tension and energy. It allows us to take advantage of better wetting properties, right? Higher spreadability. With the high bond strength, we can start thinking about heat stability. That's an application that we go into a lot, and weather resistance. Because that bond is so strong, you aren't as sensitive to UV radiation. Silicones are biocompatible, so we know that they're used in the cosmetics industry. And then because you have these R groups on here, you can now begin to functionalize it and make it compatible with organic materials. And so we get into, say, using silicone materials alongside other traditional organic materials. So how do we get and make silicones? It actually starts from quartz. So quartz is a crystalline version of sand. We mine quartz, and then you can cook it with a carbon source so that you remove the oxygen and purify silicon metal that you can find on your periodic table. And we take those hunks of silicon metal. I used to have a piece on my desk, and I've lost it at an outreach activity. But you can take these hunks of silicon metal and grind it down to a very fine powder. And then you can take that powder and react it. And so we pick up the silicon-silicon bond and replace it with other bonds so that we can use these resulting silanes as monomers for our polymerization. So we often react the silicon metal with gases like methyl chloride so that you generate chlorosilanes with some methyl groups on them. And so we take these chlorosilanes and you can separate them out based on their boiling points. And then you can wash them with water to hydrolyze the silicon chloride bond and turn it into a silicon hydroxide bond. And from the silicon hydroxide bond, you could begin condensing these monomers together to make these polymers. And so this is the basis of how we generate our silicon polymers. Now, when we talk about silicones, we have a nomenclature that was actually started by General Electric. And so this nomenclature allows us to describe the building blocks of silicone polymers. And we use it to describe the number of oxygens on each silane unit. And so I'll note one thing, that whenever you are building a polymer, again, these polymers are built through an silicon oxygen silicon bridge. So every oxygen is shared. And that's why you have designation there. And so if we look at the number of oxygens on each silicon atom, that will help us to describe it. And so for one oxygen, it's monofunctional, M, 2 oxygens, difunctional, D, 3 oxygens, T, and 4 oxygens, Q. And so now, because we know that the number of oxygen is governing what the structure looks like, we can now call mixtures of these monomers, and we can know what the structure looks like. So if somebody told me that I'm working with an MDM oligomer, right? I know that in the middle is a D unit and it's flanked by 2 M units on either side. I know what the structure looks like. And we can expand that to include polymers as we expand the number of D units there. And we can also just have a purely D type material, which would be a cyclic material. So one thing that I'll note is that these M's, because you can only bind through the oxygen, they are often used to cap a reaction. So M can only bind one time, and it's often used to cap a polymer. D, on the other hand, can bind through both of the oxygens. So Ds can grow infinitely long strings, right? And so those would be our linears. If a D string backbites upon itself, so that 2 of the oxygens on the same string attach, they'll form what we call cyclic materials that you get here. It's interesting when you get into 3 and 4 oxygens, because you then begin to make networked structures, also known as resins, and that's the space that I personally work in. So thinking about the properties of these monomers, and as we use them to form polymers. So when you're down on this end with a high amount of M and D units, you have more organic nature because of the high presence of these organic groups on your polymer. And so these are often very soft and flexible materials. If you are familiar with the term PDMS, polydimethylsiloxane, that is made up of D units and can be capped with these M units here. So it's a soft, flexible material, often with the lower glass transition temperature. As you begin to increase the amount of oxygen, you actually make this more inorganic. And so you increase your glass transition temperature, but you also increase how hard or brittle these materials are. So when we're thinking about resonant structure, they are generally solid materials, whereas PDMS are liquid materials. So at Dow, we take advantage of the functionalization of these silicone materials, right? So there's a lot of different ways that we can functionalize these monomers in order to build polymers with different properties, and we take full advantage of that. And so we have 3 axes here, which look at specific properties that we take advantage of. And the first one is molecular weight. So if we think about polymers, polymers will always have a molecular weight distribution. And so we can actually take advantage of that in order to get certain properties. So if we think about PDMS, again, PDMS is a chain of D units capped by M units, or just D units capped with OH groups. We can change the number of D units in order to change the overall molecular weight. And as you increase the molecular weight, you actually increase the viscosity, so that you can get a list of materials that range from a viscosity of water all the way down to something that is like silly putty. So this very thick material that I have here is a silicone-based material, and it's essentially made up of a lot of PDMS chains with extremely long number of D units. And so we can take advantage of these differences in viscosities and their final application, right? So if we think of something with a very low viscosity, it'll be a volatile fluid, so it'll evaporate over time. And so we have different applications for those types of materials. As we increase viscosity slightly more, you maintain it as a liquid. And so we begin using that as lubricants or heat transfer fluids. And then as we get down into heavier materials, we start to get like gums that we often use in the personal care space. Just a quick note about how we built molecular weight. So when we first opened up, we talked about the process of hydrolyzing chlorosilanes and condensing them in order to form polymers. Well, that's how we make our low molecular weight PDMS material. But if you want to get even higher molecular weight materials, then we often use ring opening polymerizations. So these are catalyzed reactions where you take those cyclic materials and you open them up and begin joining them together so that you can get the larger and larger molecular weights. And so these are often catalyzed by a base, but there are some cases where you have groups present, like a silicon hydride bond that reacts with the base. And so you'll use an acid catalyst instead. So another another axis that we like to play with is molecular structure. And this is personally the axis that I play with the most. And so that's starting to think about how we can incorporate these different monomers in order to get different materials. So when you are strictly working with M and D, you will always form these linear chains or these cycles, and that is PDMS. Now, when you begin to incorporate T units and Q units, at least to 30%, then you begin to make silicone resins. And these are important because these are highly oxygen-rich species. And so they form these networked type structures. And we have two types of silicone resins. We have ones which are T-based. So they can be made up of any combination of these materials, but they have to have at least 30% T or Q added in. And then you have a special type of silicone resins, which are called MQ resins, and they are made strictly of M units. And remember that M units can only bind once. So you have a Q structure that grows together and you end up capping it with M units. So now you have M on the surface. And so these types of materials are, again, usually solid-like materials. They have higher TGs than PDMS, and MQ resin has an even higher glass transition temperature than T resins. And they exhibit some very, very cool properties. The reason why we use them is because they are more oxidized, so they are often more stable, right? Stable to heat and stable to degradation. So if we think about some of the applications of silicone resins, we often use them when you need to provide durability. So whether that's durability to weather, durability to like scratch resistance or heat resistance, right? So some of the areas that we use them in, if you've seen an oven or you've seen a grill, you notice that it has a coating on it or like a paint. Silicone resins are the base of those materials because they are able to withstand the high temperatures that are that it is exposed to. So we often coat cookware with silicone resin-based coatings. We also have spaces like adhesives, so pressure-sensitive adhesives, and hot melt adhesives for thinking about building applications. Again, because that bond is so strong, it's often resistant to UV degradation. So we actually use this for architectural coatings as well. A lot of our silicone resins are used to paint bridges and paint buildings, painting things that have constant interaction with the sun and harsh environment because it will last longer than some traditional acrylic-based coatings, for example. And then in the last space, we have personal care and home care. So one thing that silicone resins allow is for it serves as a film former so that you don't transfer material from one space to another. So if you think about wearing a lipstick or wearing some eyeshadow, right? You don't want it to rub off or to transfer onto a different surface, right? So we take advantage of silicone resin properties to be a film former and to keep the contents within the area that you want it to be in. So we talked about silicone resins, and silicone resins naturally has a network built into it because of the number of oxygens that it has in it. But if you think about PDMS, PDMS is just a straight chain. And it doesn't matter how high the viscosity is, if you don't network PDMS, it will maintain, it will be a liquid, right? So flow even, right? And so if you want something that is not going to flow, and it's made up of PDMS, you have to cross-link it or turn it into a network so that those molecules cannot continuously flow past each other. And so that's what it is to be, say, a rubber or an elastomer. So these are PDMS materials that have been reacted with something to allow for a branch point here. So you reacted with, and we'll talk about this in a bit, but you reacted with something that allows it to connect one PDMS chain going in one direction to another PDMS chain going in another direction so that you can create this cured network that is rigid and has stability. And so I'm sure that you all have come into contact with silicone-based materials that are the result of elastomerization or vulcanization to turn it into a rubber. And these are often found in like your cookware, right? If you have a silicone spatula or silicone baking mat, those are made this way. If you have a baby bottle made up of like a plastic type liquid, nipple that's made of silicone material, gaskets and seals that are in our cars and machinery, as well as it's used in some cosmetic additives as well. So that was molecular structure. How do we use those building blocks in order to make polymers with different properties that we take advantage of? The last toolbox that we use is organic functionality. So if you remember, I showed you a PDMS chain and it had methyl groups sticking off of it. Well, we can change those methyl groups out for many different groups, and we do. And so you can change them out for different groups and achieve different properties based on the different groups that you have. So whenever you want to make silicone more compatible with an organic surface, we will often exchange it out for something like a propyl group or like an alkyl group, right? If you want to make it a bit more temperature resistant, you'll change a methyl group out for a phenyl group, and we do that all the time. And so this is a list of some of the groups that we use within Dow and some of the groups that are actually represented in our commercial portfolio. Now you'll notice that some of these groups, it says no reactivity next to. So that is just a R group switching out for an R group, and you are not expecting any reactivity on that group. But there are some groups that we install on our silicone materials that are reactive, and we want them to be reactive and perform what we call sililation chemistry. And so those groups are represented here in bold, and we often use them for cross-linking. So in order to make PDMS curable and more stable, right? So the process to get a cure on your silicone material, your silicone polymer, is through a process called sililation. And sililation essentially is just transferring a silicon group onto another group. So you start with two species. One of them is a silicone or a silane or silicone-based material with a heteroatom that is different than the heteroatom on a species with an active hydrogen source. And we'll get into some examples here. But what happens is you have this equilibrium reaction where you are swapping out these two heteroatoms such that you essentially install this heteroatom on this silo group here. So this type of chemistry is the most prevalent chemistry when we think about silicon chemistry, and is what we use every single day. And so because it's an equilibrium reaction, you often have ways to kind of drive the reaction to favor one side and drive it to completion. So this is an example here. We start off with a ethoxysilane in the presence of trimethylsilanol, so OH group on your silicon. And so this one has the active hydrogen species, and this one has the heteroatom. So we are just going to create a siloxane bond, again, an SiO-Si bond, and drive off ethanol. So that is an example of a silylation reaction. And here are some more. So again, at the beginning, we talked about taking quartz, turning it into silicon metal, then we hydrolyze it and condense it. Hydrolyzation of your chlorosilanes is a silylation reaction. Your heteroatom is chloride in this case, and the active hydrogen species is actually water. So we're turning all of the silicon chloride bonds into water. I mean, sorry, silicon hydroxide species or silanol species. And we create HCl, which is a gas, and it is driven off through vaporization, right? So that reaction goes very quickly. It's a spontaneous reaction. It actually heats up, so you control your exotherm with ice baths or temperature control, right? So that reaction happens very rapidly. Then you can take that same material and actually react it with itself. Now, again, in one case, you have an OH group as your heteroatom, and in the other case, you have that active hydrogen species. So your OSI group becomes the species that's going to move, and we can change out our heteroatoms and create another siloxane bonds here through condensation. Now, you'll see that this reaction isn't driven to one side. These siloxane bonds are very stable, actually, so it's favored to form them. But in most cases, we're using a catalyst here to drive condensation on a faster time scale than what would naturally occur. And then we can think about building in very fun and more complex functionalities, right? So many different silane species exist, and so you can imagine adding in a number of different groups onto your silicon atom through silylation chemistry. So this type of reactivity is truly our bread and butter when we think about silicon reactivity and silicon chemistry. So this is just the last example of silylation-based cure systems. So again, if we think about, we want to add in something that can branch PDMS. So we will often have a reactant in there, which is trifunctional at least. Sometimes we use tetrafunctional, but it needs to have 3 spaces for it to bind PDMS. If it only has 2 spaces, then what you might end up doing is actually just growing a super long chain of PDMS, right? So you don't want that. You want some cross-linking. You want networks where it has a T. And so you can take these reactants here, use them as a cross-linker, and begin to build in your PDMS network, and often through the aid of a catalyst. So this is actually the type of chemistry that you use when you think about bathroom caulking, the seal that goes around your bathroom type of material. This is the chemistry that is within it. Some of the areas of silylation chemistry is it's used to treat surfaces to improve moisture resistance. So if you think about putting Rain-X on your windshield to allow the water to bead off, that's silylation chemistry, right? If you take a silicone, or not a silicone, but you take a silane with a hydrophobic tail on it, and you add it to a surface which can be silylated, then you can now have a hydrophobic surface so that water has a higher contact angle and beads off as opposed to spreading out on your surface. We often use it to improve filler or pigment dispersion. So there's many different formulations that are very complex, like the paint that's on a wall, right? You put fillers in order to get certain performances, or you put pigments in. And if those pigments have a polar surface, they'll often clump together, and so they won't disperse very easily. So we can actually silylate those surfaces in order to have better dispersion for better mixing. So this next section, I'll go into an area in the consumer and electronic space. This is not an area that I personally work in, so I would try to do it justice. And so silicones are used in a wide variety of areas. These represent only a small segment of areas that we use silicones in advanced materials. And so the one that we'll discuss today is around the consumer electronics as well as communications, and the use of silicon-based electrically and thermally conductive materials. So these are composite materials. So the reason why you would want to use an electrically conductive material or a thermally conductive material is usually in electronics when you want to avoid potentially short circuiting a electronic or having electronic overheat on you. So in all electronic spaces, and today we'll talk only about thermally conductive materials, but in all electronics, there is a heat source. So as the instrument is on, for example, it's heating up. There's a heat source and a heat sink. And you want to pull heat away from the heat source into the heat sink. And so we have these materials that sit at the interface to help that happen. And so these materials are a very interesting material. It's a liquid that we engineer very well so that it can be easily dispensed, but once it's in place, it almost sits as a solid, right? And so these are highly filled systems. And for thermally conductive materials, we will fill them with thermally conductive fillers inside of a matrix that is our silicone material. And so there's a lot of engineering to make sure that we balance out the property. So how well it conducts thermal energy versus the actual rheology or how the material moves when it's under pressure. So again, the reason why we need these thermally conductive materials is because electronics are getting smaller and smaller. They're getting faster and faster. And as these things happen, they actually give off more and more heat. And so we have to manage the heat, or else you'll get a phone that is too hot, right? So it'll burn your face while you're on the phone talking. Or if we think about electric vehicles, right? Those battery fires happen, right? There's a heat runaway, right? So we want to pull heat away from these heat sources. And so our materials will sit in between these heat sources and heat sinks to allow efficient transfer of heat energy. And so again, Dow is really a leader in this area. And we on a day-to-day rely on these thermally conductive materials. So they're in our smartphones, again, in electric vehicles, in computing, telecommunications with 5G. It was a big enabler of that. So this is just a scheme of what it's like. So this is your printed circuit board and the substrate that it's on. So the heat source would be this material here, and our material would sit right in between the heat source and the heat sink. And some of the properties that you want for this material is you want it to be able to resist degradation on temperature cycles. So we often turn our instruments on and off, right? And as you turn it on, it heats up. As you turn it off, it cools down. And so when it heats up, the material will bend and flex as materials do. And so you're going to need your material to be able to bend and flex with it and also withstand those temperature cycles. And so there's a lot of properties that we have to make sure are met in order to sell these materials, right, in order for them to be useful to our customers. And so these are, three of the properties that we look at: thermal resistance, thermal conductivity, and viscosity. And then these are some of the testings that we do, right? So if you think about how these materials could fail, that informs the type of test that we do. So if the material is being heated out and it leaks out the sides, that's what we call pump out. If the material dries up and begins to cracking, self-explanatory. Delamination, so the material sits between two surfaces. If it releases from one of the surfaces, then it's not in contact and can't do its job. So that's also a problem. And then slump is if you have a material and it's turned on its side, if it kind of sags down, again, that also stops it from doing its job. So there's a very intelligent team that works together in order to not only make the materials, but also develop methods to test these materials to make sure that they are good to go, right? And that they are not going to fail in a high stress scenario. So we have a lot of different capabilities at Dow where you have the folks who are in the lab, you have the folks who are in our high throughput area, so they're able to take small amounts of materials and screen a different number of conditions in order to pick the best one, and that helps the foundational team go back and redo things. We have some modeling, computation, and then we actually have the application science part of it as well. So putting these materials in their actual final application and determining what factors we need to pull in order to produce specific properties. So that is a snippet of silicon chemistry. If you're interested in learning more, this book was recommended here for further reading. Silicon chemistry is very exciting and interesting. And when I came to Dow, it was my very first time doing it. So. And then I'll conclude with a plug for the Dow Best and Dow Diamond Symposium. So I mentioned at the top that how I got exposed really in depth to Dow was through the Best Symposium. And so Dow has these two symposium, which are aimed at increasing the number of underrepresented ethnic minorities in Dow. So we have the Dow Best Symposium, which is looking at folks who are in a doctoral program or a postdoctoral program. They get to come here for about a week and interact with us in different stages. And then we have the Diamond Symposium, which is intended for students who are in their undergraduate career to come here and find out about opportunities within Dow. So if you're interested in this or know somebody who might be interested in this, we have some deadlines coming up. Feel free to scan those and ask as many questions as you'd like. So with that, I will stop and I will open the floor for any discussions and try to answer any questions as best I can.
All right, thank you. What's the date again for the Diamond Symposium?
It is May 31st.
May 31st? So how does one kind of, because we have, undergrads here, how do we get involved in something like that?
Yeah, so you'll go to the QR code there. It'll take you to a link to apply for the Diamond Symposium. And it's usually you'll write in get some letters of support, obviously recommendation letters, but you'll also provide your resume as well as a personal statement just to describe more about you, more about what you do, what you're interested in, right? And with the Diamond Symposium, we are looking for not just say R&D or engineering, because those roles exist too, but it exposes the students to broader functions within Dow, like supply chain, like logistics and things like that. So that's the best way to get involved with it. If you scan the QR code, you can get more information about it as well.
Okay. Other questions? Yes, comments? Go ahead.
I was just gonna ask about like how recyclable the silicone polymers and the resins are. Like, is it possible to recycle them? Does the waste get built up?
So how recyclable are the polymers, the silicone polymers? Because you did
So that's
mention a lot about sustainable.
Yep, that's a very, very good point. So there's actually work right now going on to recycle our silicone materials. So they are recyclable, right, to a certain degree. And there's constant improvements that is happening with the science to be able to recycle it. But you can imagine, just like any polymer, right, you cleave it at the silicon oxygen bond and break it back down to your monomers. But one of the things, the issues that we run into is sometimes silicones are not recoverable. So areas that we use silicones in a lot is in, say, personal care, right? So if you think about your shampoos or your conditioners, those are going down the drain, right? Or sometimes the silicone materials that we use is in such small quantities that it's hard to recover them. So if you think about the silicones that is in your phone, there are a number of silicones in your phone or silicones in a car. So we have to not only work on the chemistry to be able to break these things down and to use them again, which we can, but we also have to work with collection, recollection of the silicone materials so that we have a source to begin to work on these materials. But it's definitely top of mind. It's definitely an area that we and others are working in. That's a very good question.
Good. You had a question, Ian?
Yeah, I'm curious the different like the creation of the silox.
Siloxanes?
Yeah, siloxanes is similar to making like silicone-based polymers. Is it a lot very different chemical? Silicon-based polymer chemistry?
Say that again?
Like, you know, you make silicon-based polymers.
Okay.
How different is that from, say, the siloxane polymer?
silica base. Yeah, silica for column chromatography versus siloxanes.
Yep. So the closest thing that you relate silica to is, say, an MQ resin. And the difference is that silica doesn't have any, silica is just silicon and oxygen. So let me go back a couple of slides. Silicon that we use in our column chromatography is just silicon and oxygen. And so it does not have those R groups on them, right? So that changes some of the properties as well. But say that you took silica and you silated the surface with M groups, right? Then you think that you would make a material just like MQ resins, but you actually don't, because the size is also different. And that's actually very important. So we do use silica inside of our silicon polymers as well. And it changes the properties. So for example, if you were to take PDMS and mix in silica, it's going to generate a very hazy material. It's going to be very opaque, like this type of material here. But if you were to take PDMS and mix in MQ resin, for example, it's going to generate a transparent, translucent, cured polymer. And so we do use silica, but the structure is different, and also the size is different. And so that changes its ability or its properties inside of a formulation.
Okay. Question?
You explain a little more about why silicone is influenced the business activity, silicone free.
So why are silicones in shampoo and I guess other consumer products?
Mhm.
And is there benefit to non-silicone consumer products?
So
Shampoo in particular.
what silicone does in shampoos is it provides slip. So silicones have, I had a slide in here, but I think I took it out. But silicones provide slip. So they're very slippery material. And we use them the most, I think, in so we use them in shampoos and we use them in conditioners. In conditioners, they are often terminated with an amine. So because the hair is positively charged, the amine is negatively charged, or sorry, reversed, right? So you will deposit the silicone onto the hair and allows the hair to feel nice, smooth, and slippery. Right. So that's why after you condition your hair, it feels really nice. It's because of the silicone deposition on the hair. There are drawbacks to silicone deposition on the hair. In that if it becomes too much on the hair, so like if you use conditioners on your hair and you go a while between washing, right, silicone can kind of build up on the hair and maybe irritate the scalp. And so that has driven folks to look at silicone free alternatives. But again, if you want the properties of your hair to feel nice when you condition it, right, then you have to think about how can I achieve the same thing with other materials. And so there's research in that area to make silicone-free cosmetic materials. There are some cases where silicones work the best, right? And so very rarely will they swap out silicone materials, but there's new materials that are constantly being made that can replace the performance of silicones. And that would also give consumers ease of mind too, because that's very important.
Mhm. Okay. So I have a strange question, actually. Where do you get the sand from? Do you guys do this, do you at Dow actually take the sand and do that reduction process? Or is it
So we don't,
another company?
yeah, we do the reduction process. We actually get it from quartz mining. So we mine our quartz. There are several locations around the world. One of them is down in Latin America. We mine our quartz from quartz
Okay.
mines, and we use that because starting from quartz as opposed to sand is obviously starting out cleaner. So you'll have less.
Okay, I
higher yield.
never really learned or knew about quartz mining. So the number of different places, including the US, or are they
I don't
most?
I don't believe we have quartz mines in the US.
Oh, okay.
Yeah. But yeah,
Interesting.
we mine our quartz and then we um, cook it with carbon sources. And so that's another area of sustainability, right? If you think about the source of carbon that you use, right, and making sure that it's a renewable source or you're investing in that area, that's something that's top of mind as well.
So that, yeah, I had some questions on the sustainability. So in many of these reactions to make silicones, what are the typical byproducts and how do you handle the byproducts?
So in cases of, say if we think about going from silicon metal to our methyl chlorides, some of the byproducts that we can get are often these methyl chlorides are like different methyl chlorides, but you can also get disilanes. So a silicon bound to a silicon, right, directly. And so those types of materials, we actually try to find ways to use them.
Okay.
And react them further. Other times you can recycle byproducts back into the reaction in order to drive them over to completion. So
So in these reactions, you would probably be producing like acid, HCl or something. Do you guys try to reuse the HCl for other?
yep.
Okay.
So one of the gases that we react is methyl chloride. And then another gas that we react with is hydrochloric acid. So you see hydrochloric acid actually is a product of the hydrolysis process. And so we actually just combine that with methanol and make more methyl chloride.
Okay.
Yep.
Okay.
So we try to, as much as we can, keep things recycled and internal, because not only is it good for sustainability, right, but it also keeps costs down, which is big.
Okay. Other questions? All right, thank you so very much. I think we all are a little bit more knowledgeable today about silicone chemistry.
Very
Thank
good. Well,
you.
I'm glad. Thank you all again for having me.
All right, thanks.
And we'll be in touch soon.
Okay, take care.
Have a good one. Bye-bye.
All right, bye-bye. So thank you guys for being a lot more attentive and focused. And the result was more people asked questions. I should have been asking you guys this a long time ago.